Hi, I wanted to give you an explanation of essential question number 2, version 9 in the fall of 2011. So let's start with the cash flow here. We've got it set up so that there are 3 zeros here in periods 0, 1, and 2. Then we have this thing that looks like a constant series, and then we have something which falls like a linear gradient because it's going down by 1 every single time. And then it kind of changes pace, and we've got something that goes down by 2 each time. So there's another linear gradient there, it's just looking a little different. So the way I'm going to arrange this story is that I am going to say that this constant series right here starts at 5, extends all the way out here, and goes all the way to, let's go ahead and make it time period 10. So this goes from 5, 4, period 3, all the way to time period 10. We've got a linear gradient series which is going to hang down below it, 2, 3 of those, 4 of those, and then we've got this other segment over here which is going to be its own linear gradient series, and because it starts at 0 it doesn't need to hang off anything. So let's start our notation going. We're looking for the present worth. Let's grab the constant series first. So it's 5 high, and there's 1, 2, 3, 4, 5, 6, 7, 8 elements there. So we're looking for P, given that we know A. Here's the I, it's 8 long. We still have to time shift that, so I'll add this in. We'll take care of that later. Then we got this linear gradient series that goes down by 1 every single time. And we'll add that in, so we're looking for P, given that we know G, I. And to do the counting right, there's 1, 2, 3, 4 of those, plus 1 for the pot, so that's 5. We still have to time shift that one right there. And then the last chunk is this this final linear gradient that's right here. It starts at 0, so we don't have to do anything funny. We just got to note that it's something which goes down by 2. So we're looking for P, given we know G. Here's the I, and there's 1, 2, 3, 4 of those. So we add 1 for the pot, so that's 5, and we've got to do some time shifting. So now let's get the time shifting part right. So remember the 5, we said that the last time that we actually saw an element in that constant series of 5 was in time period 10. Well, what you got to remember is that the n that's in the constant series and the exponent have to add up to that last time period. So what we should have there is a 2. And if you think about it, if you look over here, here is time period 0, here's time period 1, and time period 2 is basically the 0 on the sequence of 5s that's right here. So that should make sense. Now about this linear gradient sequence that's right here, the first time you see something is right here, and that's in time period 5, 6, 7. And the first time you're supposed to see something in a linear gradient series is in time period 2. So this should be 2, this should be 1, this should be 0. So it makes sense for a 5 to be there. At the same time, you notice that the 5 plus 5 is equal to 10, which is also the last time you see an element of that series. So that works great. The last thing to worry about is this linear gradient sequence right here. We've already said that this is a thing which is 5 long because we counted 4 elements, we added 1 for the pot. So what we have to do now is figure out what the exponent is, and the last time we see this one is in time period 15. So if 5 and the exponent have to equal to 15, we know that we should be having a 10 right here. And if you think about it, this also makes sense. In a linear gradient sequence, the first time you see a value is in time period 2, the one next to it is 1, and the one next to that, well that's the 10, is time period 0. And that should be a nice explanation to essential question number 2, version 9, in the fall of 2011.